Hello everyone and welcome to Sky Scholar. Today I wish to continue our analysis of the Fraunhofer and second solar spectra by focusing on beryllium, the first of the group 2A elements. You recall that I initially presented the Fraunhofer spectrum in this video. During the past month, the second solar spectrum has been introduced in these two videos. Now, before we examine the spectra for beryllium, one should recognize that astronomers have long questioned the extent to which beryllium, like lithium, might be destroyed in the solar interior. That is because the light elements, namely lithium, beryllium, and boron, are all thought to be annihilated when subjected to the high temperatures within the interior of gaseous stars, as one can learn in these papers. The destruction of lithium is thought to require temperatures of only 2 million Kelvin, whereas more than 3,600,000 Kelvin are needed to destroy beryllium. Therefore, it was argued that nuclear disintegration of beryllium must take place deeper in the solar interior than required for lithium. According to the Standard Model, slow mixing on the Sun did not allow sufficient time since the formation of our star for destruction of beryllium to take place. Early works, such as this one, concluded that very little destruction of beryllium has taken place on the Sun. Its relative abundance approximately matched that determined by examining the chondrites. Conversely, lithium abundances on the Sun were much lower than seen in the chondrites. Still, modern studies of Sun-like stars have found several examples with great depletion of beryllium. The exact mechanism responsible remains in question, but the rotational mixing available in these objects was argued to be more elevated. All of these arguments, of course, including those relative to final abundances, ignore chemistry. In any event, most astronomers are very pleased with the fact that the currently accepted beryllium abundances generally agree with the values determined from the chondrites. This is true despite the reality that the two may be completely unrelated. Unlike beryllium, lithium values are much lower than what is found in the chondrites. Recall that relative photospheric abundances were discussed in this video. In Lauder's Table 4, the log of relative abundance for beryllium is only 1.4. Such a low value for beryllium is precisely what is sought by astronomy and will act to bias assignments against beryllium lines. After all, if beryllium abundances are low, the elements should not be available to populate the Fraunhofer spectrum, whether with atoms, ions, or molecules. In a sense, acceptance of the standard solar model requires to some extent that beryllium relative abundances remain low. The second problem for beryllium is that it has a rather elevated first ionization energy at about 9.3 electron volts. Yet you recall that in the first video on the second solar spectrum, the lines formed in the chromosphere had first ionization energies of only 5 or 7 electron volts. With beryllium, we have an atom that has much higher first ionization energy. That becomes important if lines from beryllium-2 are actually present in the chromosphere. Solar physicists accept a temperature of only about 4,000 Kelvin for this region, but beryllium requires much higher temperatures for ionization, if only temperature, of course, is at play. If chemistry assists in ionization of beryllium, then the presence of beryllium-2 in the chromosphere would have much less to do with temperature. For now, remember that what is seen relative to beryllium might be providing clues relative to other elements as well, as we shall explore later with helium. If you examine Charlotte Moore's tables, you will find that she lists the following 9 transitions of astrophysical importance for the neutral beryllium-1 atom. I also quote the corresponding wavelengths from the NIST since we want to know the accepted modern values and their transitions. I add one more transition, namely a forbidden transition from the closed S2 shell of beryllium-1. Let us take the time to examine each of these wavelengths in the Fraunhofer spectrum and see what might be gathered about beryllium-1. But before I begin, I wish to highlight one important point. Often a line in the Fraunhofer spectrum can be attributed to 2 or more elements because they possess transitions with essentially the same wavelength. In that case, all the candidates should be listed for an individual line. One species should not be excluded at the expense of another, such that all possible candidates can be considered. So now, let us begin. Of course, this effort is part of the series on the second solar spectrum, but only a couple of lines of beryllium are assigned in the spectrum provided by Gandorfer. The assignments and transitions can be seen in this spectrum. The lines of interest are at 3321.044 and 3321.424, and there are no assignments competing with beryllium. In 1954, it was reported that a beryllium transition at 3321.347 was clearly seen on the Sun, as one can learn in this paper. If one examines modern values, two possible beryllium transitions are within a few hundredths of an angstrom of the first line, namely the beryllium-1 transition listed by the NIST at 3321.011 and 3321.079 angstroms. Then there is a beryllium-1 transition listed by the NIST at 3321.340. That is less than 1/10 of an angstrom away from the second line. In the second solar spectrum, these transitions for beryllium-1 are labeled in the Fraunhofer. If the second solar spectrum is carefully analyzed, there does appear to be a small polarized signal which one can assign to beryllium. At least that was the belief when Gandorfer labeled the accompanying Fraunhofer spectrum. Next, have a look at this spectrum and the small line at 4407.936. The line is unassigned either in the Gandorfer spectra or in the Fraunhofer data set provided by the Paris Observatory. Yet a beryllium-1 transition exists at 4407.935. That is only 1/1000th of an angstrom away. So why is the line unassigned? It is not difficult to argue that this line should be assigned to beryllium-1. There can be no proper scientific justification for not labeling such a transition. The agreement is simply too good. Next, here is another unassigned line. Beryllium-1 has a known forbidden transition at 4548.538 angstroms, which differs by less than 4/100ths of an angstrom from the line at 4548.578 angstroms. In this case, the beryllium-1 line is forbidden because the spin of the electron is changing during the transition, as the term symbols from singlet S to triplet P reveal. Such a transition is not allowed according to the selection rule that delta S must be 0. As a result, such lines are often very weak in laboratory spectra, with Einstein coefficients AKI having negative exponents. In this case, the Einstein coefficient is only 4.2 times 10 to the minus 1. That is substantially lower than typical coefficients for absorption lines with exponents like 10 to the 7th or 10 to the 8th. The weak Einstein coefficient in the laboratory is reflecting the fact that this transition is expected to be weak because it is forbidden. Yet on the Sun, the transition is clearly visible. This transition is also interesting because it arises from a closed shell. Yet beryllium is enabling the transition to occur by using a forbidden process, a clear sign that coordination chemistry is at hand. There can be no other explanation why such a weak line in the laboratory would be enhanced on the Sun. In fact, on the Sun, there are numerous forbidden transitions, and many are extremely powerful. So there is no reason to ignore a forbidden transition from beryllium-1. As a matter of fact, it is likely that all forbidden transitions in the chromosphere and corona are manifestations of chemistry, as I've tried to highlight in the past. This is why transitions which should be relatively weak become amplified. The act of coordinating an atomic excited state could very well be acting to increase the probability of a forbidden transition. That is why they are so prevalent in astrophysics. Chemistry is going on here, not just physics. In any event, there are many lines assigned in the Fraunhofer spectrum which possess similar or greater disparity of wavelength. Yet this beryllium line is not assigned. Here is another example, this time with a 6/100th of an angstrom disparity. The line is unassigned, yet it deserves at least a question mark relative to beryllium-1. After all, the line is listed in Charlotte Moore's table, and she only selected a few transitions out of hundreds possible. There is one other interesting case relative to beryllium-1, namely the line at 3515.532 angstroms. This transition is assigned to iron-1, but the closest lines in the NIST table for iron-1 are at 3513.8177, 3514.6270, 3516.4087 and 3516.5572 angstroms. None of these lines come close to the needed assignment, yet a beryllium-1 transition exists at 3515.539. That is only 7/1000th of an angstrom away. Now, it is true that other depositories of transitions for iron 1 may well exist besides the NIST collection, but one has to question why the needed line was not present in the NIST table, as it contains over 10,000 iron 1 transitions. In fact, in this figure, only the iron 1 line at 3514.636 can be found in the NIST table. The other three are not listed. Now, along these lines, a note of caution. Astronomers often shift the wavelengths of lines obtained in the laboratory to what they perceive would be appropriate conditions under vacuum. These are theoretical arguments. It would be much better to simply acquire the needed spectrum under vacuum. In any event, such arguments are weak at best, since one of the iron lines exactly agreed with the solar transition. Whatever the case may be, the beryllium transition at 3515.539 at the minimum should be listed next to iron 1 for the assignment of the line at 3515.532 angstroms. To act otherwise promotes a bias relative to beryllium assignments, which holds no place in science. One must make the assignment and let other generations know of the possibility. Again, the transition for beryllium at 3515.539 was included by Charlotte Moore in her table. There are three other beryllium-1 transitions listed by Charlotte Moore, but no evidence of these transitions are found either in this spectrum, in this one, or in this one. One thing is certain, there are several possible beryllium-1 lines, and the astronomers have systematically downplayed the assignments. Some of these, after all, were clear with no possible other candidates. Most notably, this included the beryllium line at 4407.935, versus the Fraunhofer line at 4407.936. This line is unassigned both in the French spectrum and in the Gandolfer spectrum. Yet it differs from a beryllium-1 transition by only 1/1000th of an angstrom. The line at 4572.604 differed from the beryllium-1 transition at 4572.666 by less than 7/100ths of an angstrom. Yet the line remains unassigned. Finally, the forbidden beryllium-1 line at 4548.538 in the NIST tables versus the line in the Fraunhofer at 4548.578 differed by only 4/100ths of an angstrom. Yet the line remains unassigned. All three of these deserve to be assigned, and the absence of such assignments provide clear evidence of bias against beryllium by the solar astronomers. Now let us consider beryllium-2. Here are the transitions listed by Charlotte Moore. There are two very well-known transitions for the beryllium ion at 3130.4219 and 3131.0667 angstroms. You can see the lines here in the Fraunhofer. These assignments are long-standing, and the lines are clearly seen in the French data. If one examines Moore's table for beryllium-2, these are the only transitions for this ion still believed to exist on the Sun in this region of the electromagnetic spectrum. These two lines are extremely important because their formation requires temperatures which are much more elevated than the 4000 Kelvin currently believed to determine which transitions will be observed in the chromosphere in the standard model. Yet these are in fact chromospheric lines, and their presence acts to counter the belief that the production of electronic transitions in this region of the Sun is solely related to temperature. Again, chemistry is at hand here, and that is why one can see beryllium-2 lines in this region of the Sun. We continue with more lines from beryllium-2 and proceed with the transition at 3274.674 in the NIST table. In the Fraunhofer, there is a strong line which is nearly coincident at 3274.668 angstroms. That line, however, has been assigned to calcium-1, which is also coincident at 3274.67 angstroms. Yet the beryllium transition is not even mentioned, even though it is essentially identical. Surely this transition should be mentioned, but it is not, even though it is only 6/1000th of an angstrom away. Next, have a look at the beryllium-2 line at 5270.284. There is a line in the Fraunhofer at 5270.272, which is assigned only to calcium-1 at 5270.27. There is an adjacent second line at 5270.356, which is currently assigned to the 5270.356 0.356 transition of iron 1. Despite these assignments, one cannot exclude the possibility that beryllium-2 is also found in this region. It should therefore be labeled even if it cannot be resolved. Next, have a look at this weak shoulder located at 3241.804. This shoulder is not assigned either in the Gondorfer spectra or in the French Fraunhofer data. The line is nearly coincident with a beryllium-2 transition at 3241.827, yet again no assignment is made. Now have a look at the very weak region in the baseline of this spectrum at 4361.04. Currently, this is a rather broad feature assigned to cobalt-1 in the Gondorfer spectrum. However, the closest cobalt-1 line in the NIST table is at 4359.427 angstroms. That line would appear to the far left of this figure. Once again, there could definitely be another source of cobalt-1 data, but the line in question is not reported by the NIST. Conversely, there is a beryllium-2 transition exactly in this region at 4361.032. Finally, we come to another broad and weak baseline feature, this time at 4673.44 angstroms, which is assigned to the carbon dimer. However, there is a beryllium-2 transition almost exactly coincident at 4673.423. Again, no mention is made of beryllium-2 in this case. So when beryllium is examined, both for the atom and for the ion, we find numerous transitions which have not been assigned in the Fraunhofer spectrum, but whose positions are very nearly coincident. This is not an accident. The solar physicists do not want beryllium lines on the Sun, and it certainly appears that they have biased their assignments against those transitions. If one examines the assignments in the spectrum, it is clear that when two ions are coincident, then both are usually listed. Astrophysics can offer no justification to move away from the practice relative to beryllium other than their preconceived notion of relative abundances and required ionization potentials. Relative to beryllium, it is also important to consider that beryllium hydride has been found in sunspot umbra as reported in these two papers. Here is the relevant quotation. In the present study of 812 laboratory lines, 359 lines were found present, and most of the missing lines were accounted as merged with nearby strong atomic or other molecular lines due to magnesium hydride, iron hydride, calcium hydride, and titanium oxide. It can therefore be stated without doubt that these additional beryllium hydride isotopomer lines are present in the observed umbral spectrum. Now ask yourself why two reports from some of the top spectroscopists in India had to be published in a Serbian journal. Why not in the Astrophysical Journal or a journal like Solar Physics, as happens for every other major discovery relative to new molecules on the Sun? The answer is simple. Journals like the Astrophysical Journal and Solar Physics do not want to hear about the possible presence of beryllium hydride on the Sun because that casts doubt with reference to the relative abundances calculation and their models relative to chromospheric densities. After all, one cannot make beryllium hydride unless sufficient densities of reactants are present to enable the product formation. In the end, the standard model advances extremely low beryllium abundances on the Sun, and that implies that beryllium hydride cannot be present. But the fact remains that it is present, and that must make many astrophysicists extremely uncomfortable. So congratulations to the editors of the Serbian Astronomical Journal for the courage they displayed in publishing these beryllium hydride results. Sometimes the truth can be found in the most unlikely place. Well, that is all for now. I hope that this is starting to make everyone realize that not all is well with solar physics. The biases afforded by our own models and theories now govern what is accepted. In this regard, one has to wonder how many molecules have actually been observed on the Sun, but whose presence has been denied by interested reviewers. I had hoped to cover the rest of the Group 2A elements in this video, but that will have to wait until next time. So if you enjoyed the presentation today, promote the channel, mention the videos to your friends and to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the Sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on the next video.